finally, the last part of this lecture, I'd just like to share with you some food for thought, which comes from a wonderful paper of our own Matt Lieberman, which discusses possible unintended consequences, or at least that's how I interpreted this, of the direction that the field is taking in terms of correcting for multiple comparisons. It seems to me, and I think this is the heart of their argument, that we are over-obsessing on controlling for type 1 errors, which is very important. We do want to control for false positives, obviously, but we are over-obsessing the extent that we're going to control for type 1 errors, and I think this is sort of really the heart of their point, might have unintended consequences. So what is the cost of this, really cranking the dial in terms of how conservative our analysis will be in terms of type 2 errors in order to control for the type 1? Indeed, they say, well, the first obvious problem with being so sort of we're cranking the dial on our p-values with making them so stringent is that we are obviously increasing type 2 error, meaning we're losing power, we're losing sensitivity. And they make this example. Take a real effect, in fact, take a large effect, R square of 0.25, that means a correlation of 0.5, and 20 participants. If you were to threshold that effect at 0.005, the likelihood of detecting it would actually just be just about 30%. So giving you just about 70% type 2 error. If you thresholded it at 0.001, the likelihood of detecting it is just about 14%, leaving you with an 86% of type 1 error, of type 2 error, excuse me. If you thresholded it at an even more conservative 0.0001, the likelihood of detecting it is 3.5%. I mean, very clearly, as we crank up the dial on how stringent we want our correction to be, we're losing opportunity to find real effects. So we're trading off, and I think the argument is in a very unbalanced manner. Just whatever we do, let's not have type 1 errors. In order to follow that point of view, we are trading off a pretty harsh amount of type 2 error. So the emphasis on controlling so tightly type 1 error has this potentially devastating effect on the ability to detect true signals. And see, there are a number of consequences to this. First, there's just a bias towards large and obvious effects. I mean, sure, it'd be wonderful if we all could run 500 subjects. That is the one thing that would help both type 1 and type 2 error at the same time. However, unless you're a very established investigator and unless you have good NIH funding, you're very unlikely to be able to do any more than 20, 25 participants. So as p-values get more and more conservative, right, you probably, using thresholds that are that conservative, you can probably only get some data and some results for very large, very obvious effects. In their calculation, if using an uncorrected value of 0.001, you would need a Cohen's d of at least 1.85 to get an effect with only 20 participants or so. So in a sense, it's biasing our research towards large obvious effects, not towards more subtle and for some much more interesting effects. I mean, if you think of it, and on top of it, and here you can see the slant of the article coming from a specific subset of the field of neuroscience, which is the social affective neuroscience. Because this might affect them, although I think it affects some aspects of cognitive neuroscience just the same. This type of very stringent approach to thresholding does bias, because it favors these large obvious effects, it biases against the more subtle type of effects that are more characteristic of social affective neuroscience, I would argue, of some higher cognition, also sort of higher cognitive processes. Essentially, the more you go away from sensory processing and sensory responses, the more you get penalized by the by this very stringent approach to managing type 1 error. And there are at least two reasons in their sort of argumentation. First, variability. I mean, low-level stuff, look, if you blast somebody's visual cortex with a flashing checkerboard, or if you get somebody to do finger tapping, it just has low cognitive and temporal variability. If I blast your visual cortex with a flashing checkerboard, your visual cortex will turn on right there and then. And as soon as I stop, your visual cortex will stop. And if we do motor tapping and I tell you start tapping, you will start tapping right away. And also, you will be able to maintain that. Your brain will keep responding throughout the task. And then when I say stop, you will stop right away. So the onset and offset of sensory motor stuff tends to be pretty systematic. Compare that to the high trial-to-trial variability of the onset and offset of stuff like emotional reappraisal, forming judgments. That kind of cognitive process is just not, it just doesn't have that stability. That's just the nature of the beast. It doesn't have the stability of sensory motor processing. So you're going to get much greater variability. Because you get much greater variability, you're going to kill off these effects much faster compared to sensory motor if you make a very stringent correction. Similarly, or rather compounding the issue, and this truly is an aspect fairly special to social and affective neuroscience, which often cares about regions that just so happen to be nearby dropout zones. For example, ventromedial prefrontal cortex, an area that is very interesting for a lot of social and affective studies, and sort of the more ventral part of frontal cortex, so the orbitofrontal cortex, sort of those areas. They just happen to be, so unfortunately, nearby boundaries. So for example, just under the sinus. And so they're susceptible to signal dropout, which means not only these are very variable trial-to-trial type of processes, and that's just the nature of them, they also happen to be in bad parts of the brain if you're doing imaging. Same is true if you care about the very ventral part of temporal cortex. So perhaps if you're doing some language stuff, particularly on the receptive end and on the semantics end, you're just above the ear canals. So also you're going to have these dropout issues. So there are these two issues that are conspiring to hurt anything that is not, a pretty robust and systematic and very stable type of processing, which is more typical of sensory and motor type processing. And finally, and this is, to me, one of the most powerful points of their argument, there's a problem with meta-analysis. See, we all say, oh, let's just do meta-analysis and that will sort out the true effects from the non-true effects. Well, this works well for type 1 errors. Because see, type 1 errors, not only we control them, that's what we control in our studies. We don't control type 2 errors, meaning we set out to control the type 1 error. Even if you were to get a type 1 error, it's self-correcting over time because someone else is going to do a similar experiment. They will report a different result, and they will fail to replicate. And over the body of literature, it will turn out that, well, that one experiment was a false positive. Fine. As scientists, we accept that there is a chance of that false positive. But the beauty of meta-analysis is that they correct for false positives. What meta-analysis do not do is correct for false negatives, because the false negatives never make it into the literature. So there's no amount of meta-analysis that you can do to recover a false negative and turn it into a real activation. So in this sense, the argument might be, look, we're better off having false positives, knowing full well that a few years down the line, somebody's going to do a meta-analysis and they might say, look, your study was great and all, but that was probably just a false positive because these other 5 studies did a similar type experiment, but they didn't get that activation. right? Again, type 1 errors are self-correcting in that way if we do meta-analysis. Type 2 errors never self-correct. So we would be better off, this is the argument, having more type 1 errors in favor of reducing the type 2 errors. What are the solutions to this? Well, sample size, duh. That's the only thing that is going to save us with respect to both type 1 and type 2 errors. Or we decide that only 3 labs in the country ever get funding to do studies with 500 participants, which would be wonderful, perhaps, but then we'd have to pick who those 3 are, and I'd better be one of those 3. Or, you know, perhaps we move towards a broader view of assessing significance that, of course, has to be at the single study, but also takes into consideration the fact that we accumulate literature over time. And so maybe we might allow to have a little more type 1s in favor of less type 2s, knowing full well that as we collect more studies on the same thing, we will correct sort of the record, or rather we will aggregate into a synthesis of multiple studies. And this would allow to correct for the type 1s and would allow type 2s to then emerge. So where do we go from here? Well, it's hard to say. My guess is we're going to go towards some, you know, bigger, better, faster, cooler strategies of thresholding. I would point out that there's a couple ones that seem to me like extremely promising. Not quite usable at present, but there's a strategy called hierarchical FDR. It's impractical now because it requires you to have other data or to make more assumptions. But the idea, which I find very appealing, is that we would probably apply a first threshold to get clusters. That would be a first FDR threshold to get clusters. And then what we would do is we would go inside those clusters and trim those activations to find those that are the voxels that are really the significant ones within each cluster. That'll be a wonderful way forward. For now, it's impractical, but it might be a good way forward. And then, of course, you know, who knows? Maybe it won't be about thresholds at all. Thresholding is a very nonlinear operation to do. Maybe we will all just upload our unthresholded t-stat, and you know, we will slowly accumulate it over time, and that will lead us towards a real, you know, the real result. And of course, you know, maybe it won't be about this paper or that paper, but it will be about obviously replication. And if that's the case, though, we will have to find how to trade off type 1 and type 2 errors to reflect this. Okay, let me close with a final recap of the second half. So how are you going to threshold your study next time you do a study? Well, look, definitely not uncorrected. That's a no-no. And I don't think any journal is going to accept an uncorrected unless there are good reasons for it. The ad hoc approach, sort of the 0.01 uncorrected and then some number of contiguous voxels, from a type 1 error point of view, definitely not, because you risk getting crazy inflated type 1 errors. From a type 2 point of view, well, I don't know, maybe if you plan to do another 5 experiments and then you can collate them all in a meta-analysis. Or you can think of it this way: what if you keep doing sort of this ad hoc and you do keep replicating it time after time? Then it can't just be random noise that is leading to this replication. Voxel-wise, family-wise error, Bumferoni, and nobody does it. And you shouldn't, because the hypotheses of it are violated anyways. Random field theory at the voxel-wise level, really conservative. As far as I know, nobody does it. Cluster-wise, family-wise error, it seems to me this is one of the 2 most popular approaches. Parametric one, so based on random field theory, I think this is the most stringent one. To me, the data, at least the raw data, says that like minimum is 0.005, so I think that's a 2.7 or 2.9, one of the 2. That might be still okay. However, I think the Eklund data tells us that if you're using FSL versus SPM versus AFNI, it does make a difference. So you want to keep that into account. I would suggest using FSL just because the way in which it does the group level analysis is just much better in terms of handling both the within and the between variants. And also it gives you the option of doing, of downweighting outliers automatically. Or just use non-parametric approaches. It might be the way of the future. I don't know. I wouldn't hold my breath just because randomized takes a really long time. But this day and age, particularly if you're here at UCLA, you just launch a command. You launch randomized parallel. It just sends it to all the nodes that are available to you on Huffman 2, and then go do something else for a day or two. And then you're going to get your result. The cost of it is so low to us that maybe we should be doing it. Or use Broccoli, which can run on a GPU and is extremely efficient. Sure, it is less efficient than parametric analysis if the hypotheses are met. And you should be careful of knowing how to do your permutation if you have any type of serial correlation. You know, if you have longitudinal designs, if you have any other type of structure that leads to correlation within your observations. And also I would suggest if you use FSL and you use randomize, there's this tool called threshold-free cluster enhancement that allows you to just say, give me 0.05 corrected, and you don't even have to specify the cluster determining threshold, which is wonderful. It has its own assumptions, but they've been pulled out of data and they've been placed there for you. Finally, maybe FDR. And sure, at least it's a voxel-wise, which allows you to point at voxels. On the other hand, although it might be a good compromise between type 1 and type 2, it's hard to point, as I was saying earlier, to point at a voxel and say, I don't know, maybe this one is significant, or maybe this one here is the 5%, I can't tell. So it has sort of that downside to it. And finally, perhaps someday the cluster, the hierarchical FDR, that'll be really great if it were worked out. For now, it's just not really viable. But at least this is the panorama of your options. So how are you going to threshold your next group analysis? My take, you're probably going to do it exactly the way you were doing yesterday. However, you now understand much better the issues that go into doing group analysis and thresholding. Should reviewer number 2 ask you just the same, should it be the same reviewer number 2 that I had quite a few times?